Hello everyone. In this video, we will be discussing about mathematical induction for the IB Diploma Math Higher Level course. There are 5 key steps to mathematical induction. The first step is to let a statement P of n conjecture that the mathematical statement is true for given conditions. The keyword here is given conditions. You have to follow what the question asks you to do. The second step is to verify that Pn is true for one of the given conditions. This is known as a basic step. Now here, one of the given conditions, we usually use n equals to 1, but again, some questions put a restriction by saying, for example, n has to be greater than or equal to 4. So again, it depends on the question. So read the question carefully, okay? And the third step is to assume that pk is true for the same conditions. Now this step is known as the induction hypothesis, and the keyword here is assume. This is really important. A lot of students use statements such as let n equals k, and if you say that, the mark scheme explicitly says that they will not give you a mark, so you have to assume that this is true. After step 3, you go to the actual induction step, where you use the result from step 3 to prove that when pk is assumed true, then pk plus 1 is also true. If you successfully prove that pk plus 1 is also true, you can write your conclusion. Now the conclusion would be p1 is true. When pk is assumed true, then pk plus 1 is also true. Hence, by mathematical induction, Pn is true for given conditions, and then you've successfully finished your mathematical induction. There are mainly 4 types of questions which can be tested in the induction part of our IB exam papers. One of them is the sum. So without further ado, we will try one of the questions for mathematical induction. So this is one of the questions we will attempt in the video. So this question wants us to prove by mathematical induction that the sum of this expression, so r plus 1 times 2 to the power of r minus 1 from r equals 1 to n is equal to n times 2 to the power of n for n being a positive integer. So let's start with step 1. Let Pn conjecture that the sum of this expression from r plus 1 to r minus 1 equals n times 2 to the power of n for n being a part of the positive integers. Then in step 2, we check with one of the numbers in the conditions. Now, because it's a positive integer, we'll be using n equals 1. So check with n equals 1, so which is the same as p1. So for the left-hand side, it would give us, so 1 plus 1 times 2 to the power of 1 minus 1. Now we know that this is equal to 2 and this is equal to 1. So 2 times 1 equals 2. And the right-hand side will be 1 times 2 to the power of 1 equals 2. So because left-hand side and the right-hand side is the same, we write that left-hand side equals to right-hand side. So P1 is true. Next, we move on to step 3, where we say let pk, oh no, not let. As I said, this is a common mistake made by many people, so don't write it, okay? So assume that pk is true such that so we replace n with k in the original expression, so it becomes the sum of this expression from r equals 1 to k for r plus 1 times 2 to the power of r minus 1 equals k times 2 to the power of k for k being a part of the positive integers. Next, we need to show that, so write that, need to show that p k plus 1 is true, so it would give us the expression of the sum of this expression, r equals 1, k plus 1, r plus 1, bracket 2r minus 1 equals k plus 1 times 2 to the power of k plus 1. So we need to show that this is true. So how do we do it? Well, as again, start with the left-hand side. So left-hand side, we have the sum of this from r equals 1 to k plus 1, r plus 1 times 2 to the power of r minus 1. And then write the right-hand side too, just in case you don't get confused and you get an idea of where to go. And the right-hand side would be k plus 1 times 2 to the power of k plus 1. Okay, now I'm going to divide this section so it doesn't get too messy or confusing. So if we simplify this expression for left-hand side, we can actually rewrite this because it's k plus 1, right? This expression is the same as r equals 1, k, r plus 1 times 2 to the power of r minus 1 plus k plus 1 in the position of r plus 2 to the power, times 2 to the power of k plus 1 minus 1. So what this is showing us is that this, and because from the step 3 inductive step, we know that this expression is the same as this, because you see, this is the same. So I'm going to rewrite this as k times 2 to the power of k plus 2 times 2 to the power of k, right? And now, because there's a common factor of 2 to the power of k, we can take it out. So 2 to the power of k, and if we add these up, it becomes 2k plus 2. Now, do you notice that we can still take out a factor of 2 here? So this becomes 2 times 2 to the power of k plus 1, right? Now, this expression can be simplified as 2k plus 1, k plus 1. And do you notice how this is the same as the right-hand side? So we've successfully proven that, so step 5, left-hand side equals right-hand side for pk plus 1, pk plus 1 is true. And the conclusion, p1 is true when pk is assumed true, pk plus 1 is true. Hence, by mathematical induction, Pn is true for n positive integers. And this is how you successfully mathematically conduct an induction for this question. This is another type of question that's also commonly tested. It's a divisibility result question. So this question wants us to prove by mathematical induction that 3n to the power 3 to the power of n plus 5 is divisible by 2 for n being a positive integer. So what this is saying, right? So if we start with step 1 again, let p n conjecture that the expression 2n plus 5 divided by 2, let's say it's equal to alpha, where alpha is an integer, right? Because if this is divisible by 2, it means that when you divide this expression, it should give you an integer. So this can also be written as 3 to the power of n plus 5 is equal to 2 alpha, again where alpha is an integer. So let's check this. It says for all positive integers, so we're going to use n equals to 1 again. So check with n equals to 1, so that would give us p1. So let's look at without the left hand side being needed, let's sub into the expression of n. So 3 to the power of 1 plus 5 is equal to 8. And 8 can be rewritten as 2 times 4. So, yes, this is divisible by 2. And so P1 is true. Next, we assume that PK is true such that 3 to the power of k plus 5 equals to 2 alpha. Again, where alpha is an integer. That's the same, right? And then we move on to step 4, the induction step. So here we will be writing that check if pk plus 1 is true. So we need to show that 3 to the power of k plus 1 plus 5 is also equal to 2 alpha, where alpha is an integer again. Okay, so let's do it. So if we see this expression 3k plus 1, 5, we can rewrite it as 3 times 3 to the power of k plus 1. Here, using the inductive step in step 3, because we know that 3k plus 3 to the power of k plus 5 equals 2 alpha, what this shows us is that 3 to the power of k is actually equal to 2 alpha minus 5, right? So we can sub this value here. So sub. Then it would give us 3 to the power of 2 alpha minus 5 plus 5, which is equal to 6 alpha minus, this is minus 15, so minus 15 plus 5 is the same as minus 10. And this expression can be rewritten as 2, 3 alpha minus 5, right? So divisible by 2 and pk plus 1 is also true. Then let's go on to the final step. P1 is true when pk is assumed true. Pk plus 1 is also true. Hence, by mathematical induction, you see step 5 is the same. You just have to write the same sentence over and over, but it's still required. Induction, Pn is true for n being a positive integer. Okay?